Welcome back everyone to Fly Vehicle Dynamics. This is part 2 in lecture combination of lecture 28 and 30. We're talking about longitudinal static stability, and the last thing that we saw last time was the condition for the static stability itself. And that was that Cm alpha has to be negative. That means that if there is a sudden change in angle of attack, so perturbation from the trim condition, from the trim angle of attack, then having Cm alpha negative means that a restoring moment will arise, a negative moment, forcing the nose of the aircraft down, so lowering the angle of attack. Conversely, if you had a perturbation that would decrease suddenly the angle of attack, then the fact that Cm alpha is negative, that means that we would produce, or the aircraft would produce, a restoring moment, positive moment, in order to pitch up and increase the angle of attack. Okay, so now always talking about the pitching moment, and in particular about the aerodynamic pitching moment, let's just see how that can be divided. So we can write it down as the sum of three terms. So we have a pure torque created by the wings and the fuselage. We're going to call it MACWF. So it's a pitching moment, aerodynamic pitching moment caused by the wings and the fuselage. And then we have the moment generated because of the lift force generated by the wings and the fuselage. So the moment is, of course, the force times the distance between where the force is applied, which is the aerodynamic center of the wing and the fuselage, and the center of gravity of the aircraft. The moments are still expressed with respect to the center of gravity. Therefore, we have LWF, the magnitude of the force, times the distance between the center of gravity and the aerodynamic center for the wing and the fuselage. Now, you see that this is the moment LWF times the distance x CG minus x ACWF is in the clockwise direction, so it's a positive moment. Whereas the lift that is generated by the horizontal tail, which we've indicated with LH, will cause a negative moment. And what is the magnitude of such moment is the magnitude of the force, so LH, times the distance between the point at which LH acts, which is ACH, or in other words, the aerodynamic center of the horizontal tail, and the center of gravity. This expression is valid for a small angle of attack. Now, if we divide everything by the dynamic pressure and the wing surface, so SW, we're going to find our good friend, the pitching moment coefficient. So pretty much we're going to substitute everything, all the moments and the forces with their corresponding coefficients. So MACWF becomes CMACWF, and then LWF becomes the lift coefficient associated with the wings and the fuselage. And we have CLH, which is the lift coefficient associated with the horizontal tail. This term arises because we've normalized everything divided by S W, and of course that's not how LH is defined. Well, I don't want to go too much into details of how this is derived, but anyway, it's just a non-dimensionalizing the equation for the pitching moment. Oh, another thing, we also have to make the distances adimensional. So in order to make the distances non-dimensional, we divide this x bar, xcg bar, and xacwf bar is simply the distance x divided by the mean chord of the wing. Another thing that you might ask is that where's the zero for the x? Well, could be anywhere, because in the end we're only interested in the difference. But sometimes, or very often, I should say, the zero is in the corresponds to the leading edge of the wing, so that the distance over here would be xacwf, and this distance would be xcg, and so on and so forth. Okay, as we saw for the lift coefficient and for the drag coefficient, I'm also giving you some expressions for the derivatives of the pitching moment. And all the terms here, we've already explained what they mean in part one of the lecture. So I'm going to skip over them. But I want to describe very quickly these curves. So here we have, let's take, for example, the left plot. We have Cm versus alpha, and you see that we have to fix a value for example, the incidence angle of the horizontal tail. So let's just put it equal to 0. And then we have different curves for different values of the elevator deflection. So if the elevator deflection was 0, since IH is also 0, then for alpha 0 equals 0, we have this point over here, which corresponds to exactly Cm0. Each of these three curves, they have a negative slope. It's because as alpha increases, Cm decreases, and the slope is nothing but Cm alpha. And we expect the slope to be negative because Cm alpha has to be negative for static stability. You can also see that Cm delta E is negative because if we fix a value of alpha, as we increase delta E, so I'm going downwards, but I'm increasing delta E, you see that we go from -5 to 0 to +5. So going downwards increases delta E, but we are decreasing Cm, therefore Cm delta E is negative. Similarly, we can say the same if we consider delta E equals 0 and different curves parametrized by the incidence angle. As we increase the incidence angle for a fixed value of alpha, we decrease the pitching moment coefficient. Now, the other thing is that when we intersect one of these curves, actually, could be any of them, but when they intersect Cm equals 0, then that corresponds to a trim condition, because Cm equals 0 is the trim condition. All right, so now we're going to do something that might look a little bit complicated, but it's going to actually simplify some things, because we want to find a condition in terms of geometry to understand whether the airplane is going to be statically stable or not in the longitudinal sense. So instead of dealing with two aerodynamic centers, the one for the wings and the fuselage and the one for the horizontal tail, we're going to define the overall aerodynamic center for the airplane. In order to do that, well, that is given by this wonderful formula over here. So that is what it is. We're not going to stay here and analyze it. But if we consider, so using this definition, we can rewrite the pitching moment as this much easier version over here. So the overall aerodynamic pitching moment about the center of gravity. So here, if you wish, you could add, it's always with respect to the center of gravity, is the pitching moment about the overall aerodynamic center of the airplane plus the overall lift force, which is obviously the sum of the lift generated by the wings and the fuselage and the lift generated by the horizontal tail. Here, of course, there's no vector sign, so we're talking about magnitudes, and times the distance between the center of gravity and the aerodynamic center. All right, so now if we just normalize this equation, so if we make it non-dimensional, then we're left with Cm, that is equal to Cm AC, so the pitching moment about the aerodynamic center, plus Cl times now the normalized distances, so x bar Cg minus x bar AC. Again, our objective is to find an expression for Cm alpha that relates to the geometry of the airplane. So what we're going to do now is to take the derivative with respect to alpha of this expression over here. So we're going to have Cm alpha, is by the definition, dCm partial Cm partial alpha, is equal to CMAC alpha, which is 0 because CMAC, so the value of the pitching moment with respect to the aerodynamic center, remains constant with the angle of attack. So if you take the derivative with respect to the angle of attack itself, you're going to get 0. So now we're left with, so this term goes away, and the last term is going to be Cl alpha times the distance between the center of gravity and the aerodynamic center. From what we saw earlier, or in part 1, I should say, we know that Cl alpha is positive. Remember that Cl alpha gives you the slope of the Cl versus alpha curve. So Cl alpha is positive, at least for small angles of attack. Therefore, we have a very nice expression for Cm alpha. And Cm alpha is Cl alpha times the difference between the position of the center of gravity and the aerodynamic center. Now, if we want stability, well, Cm alpha has to be negative, but Cl alpha is positive. So the only way for Cm alpha to be negative is that xcg minus xac has to be less than 0. Or, in other words, the center of gravity of the aircraft must be in front or towards the nose with respect to the aerodynamic center. And only if the center of gravity is in front of the aerodynamic center, we have static stability. If we have the center of gravity behind the aerodynamic center, then we would lose the the static stability. So let's see how this works. So let's, just for sake of understanding, consider only the wing. So let's say in case I, this corresponds to the trim condition. So we have a certain trim angle of attack alpha star, and we have a trim generation of lift L star, and a trim value of the moment with respect to the aerodynamic center, MAC, always with the star. So the overall pitching moment is MAC star plus, well, they should be trim, right? Plus L star times XCG minus XAC. Oh yeah, well, I put it over here. It's okay. Just do this. So in trim condition, the overall pitching moment has to be equal to 0. Okay, very good. Now let's say that we have a perturbation that will increase our angle of attack. So now our angle of attack is the trim alpha star plus this little increment delta alpha. So by tilting the aircraft, so by increasing its angle of attack, the lift produced by, the overall lift will increase by delta L. And so it would increase, since from the trim condition, there's going to be a restoring moment counterclockwise, which will force the nose down, so towards the trim condition again. And we can see it mathematically like so. If we have now the overall pitching moment is the trim moment with respect to the aerodynamic center, and now we have this increase in lift, L star plus delta L. So we can rewrite it as M star, so the trim pitching moment, which is 0, plus this contribution, so delta L times xg minus xac. But since the center of gravity is in front of the aerodynamic center, this difference is negative, making this delta M, so this increment in the pitching moment, negative. And therefore, it will cause the nose of the aircraft to tilt downwards. It's a similar thing if we have a decrease in angle of attack with respect to the trim condition. So if we decrease the angle of attack, then we're going to decrease the overall lift. And so the resulting increment in terms of pitching moment is positive. And so a positive pitching moment will cause the nose to go back up, and therefore the angle of attack to increase as well. All right, so this is just a few words to summarize what I just said, that the condition for longitudinal stability is the fact that the um, derivative of Cm with respect to alpha has to be negative. Okay, so with that in mind, we can ask ourselves, okay, so we need Cm alpha to be negative for static stability. What if Cm alpha is 0 or positive? Well, we saw that if it is negative, we have positive static stability. So the center of gravity is in front of the aerodynamic center. If the 2 points coincide, then we have the so-called neutral static stability. Whereas if the center of gravity is behind the aerodynamic center, so it's more towards the tail, then we have negative static stability or instability. And we can see that in terms of curves of Cm with respect to alpha. So if we have a negative slope, well, we can trim the aircraft because the line will intersect Cm equals 0. If we had neutral static stability, then the slope of the curve would just be 0. And for negative static stability, the slope of the curve is positive. Now, you see that it might seem counterintuitive because neutral stability, it seems you're not, asymptotically stable. So you're not really producing a restoring moment, but you're not diverging either. But you see that if, for example, in this case, if the point at which this line intersects the Cm axis is positive, it means that for any angle of attack, alpha, we're going to have a positive pitching moment. So we're still going to increase our angle of attack. So for any angle of attack, we have an increase in pitching moment. So the only way for to be able to trim the aircraft if we had a neutral static stability, it would be if this orange dot was here at the origin of the two axes. Okay, so the neutral stability implies, it's two things. Well, it's the same thing actually. You can either say that Cm alpha is equal to 0, or that the center of gravity coincides with the aerodynamic center. So since the second one is also a condition for neutral static stability, the aerodynamic center itself is also known as neutral point. So that's why we have this equality. And it represents, if you wish, the threshold between stability and instability. If the center of gravity, we're going to see in a few minutes, if the center of gravity is ahead of it, then we have static stability. If it coincides with it, it's neutral stability, neutral point. If it is behind, we have instability. So in general, if we are away from the neutral point, we can define the so-called stability margin to know whether or not how far away we are from neutral stability. Do we want to be near neutral stability? Not really. Well, it really depends on the aircraft as I said in the previous lecture, if you want an aircraft that is very maneuverable, then you don't want much stability. So in terms of stability margin, you would want a small stability margin. If you want instead an aircraft that is very stable no matter the perturbation, so you want a very stable aircraft without having to use controls, then you want a quite a big stability margin. So stability margin is simply the difference between AC, the position of AC, meaning the aerodynamic center, and the center of gravity, or the neutral point minus the center of gravity. All right, so if the static margin is positive, we have a positive static stability. If it is equal to 0, we have neutral static stability. And if less than 0, we have negative static stability. Now in this table here, I sort of summarized what I've said so far. So we can express the same concept of static stability using 3 parameters. So either we refer to Cm alpha. So I'm just going to read the positive static stability. That has to be less than 0, which implies that the safety margin is positive, and that the center of gravity is positioned ahead of the aerodynamic center. So this way, if we indicate the center of gravity, this usual symbol, and the aerodynamic center with the orange dot, then a statically stable airplane would have this configuration. If the two coincided, then we would have neutral stability, and in this third case, we would have instability. All right, so let's now take a look at, once again, at the equation linking Cm alpha with Cl alpha, and this distance here, which is minus the static margin. So we have that, as this equation suggests, as Cm alpha is equal to minus Cl alpha times the static margin, or the static margin is equal to minus Cm alpha over Cl alpha. Now, Cm alpha is, of course, partial Cm partial alpha, and Cl alpha is partial Cl partial alpha. So simplifying delta partial alpha and partial alpha, we have that the static margin is equal to minus Cm Cl. So what that means is that if we were to graph Cm, so always the pitching coefficient, but now as a function of the lift coefficient Cl, which is on the x-axis, then it's sort of similar behavior of the curves as we saw Cm with respect to alpha. For a positive static stability, we want a negative slope. For an unstable aircraft, we would have a positive slope of the Cm over versus Cl, and a slope equal to 0 for a neutral stability. Just one thing, if we combine this equation with Cm equals minus Cm Cl, we find that Cm alpha is equal to the product of Cl alpha times Cm Cl, which is going to be used later. And actually, we're going to use it right now, because now the question is, how can we determine the neutral point? Because now, yeah, everything's fine, a bunch of formulas, but in real life, if we had to determine the neutral point, so the aerodynamic center for the whole aircraft. How can we do that? Well, let's just try to, well, now we have to derive a couple of equations, and then we're going to get to the more practical things. So let's start by recalling the trim condition. So the longitudinal trim condition is simply Cm equals 0. So expanded in all its coefficients, we have Cm0 plus Cm alpha times alpha star, so on and so forth, but everything equal to 0. Now we're going to substitute the value Cm alpha with what we just found up here. And of course, everything else is the same. Now we're going to use a little bit of an approximation, saying that CL is pretty much, proportional to CL alpha times alpha star. So we can substitute this right here. And by expliciting the value of the elevator deflection, the trimmed value of it, that is almost the expression that we saw, that you guys are familiar with the only exception is that now we have CMCL and CL trimmed. And why do we want to do that? Well, I'm going to explain right now. But before that, let's take the derivative of equation number 5 with respect to what? With respect to CL star. So we're going to have the partial derivative of the trim condition for the elevator deflection with respect to the trim condition for the lift coefficient, and that is equal simply to minus this. If you take the derivative, this is not a function of CL, this is not a function of CL, so you simply have minus CM CL divided by CM delta E. All right, well, still, how can we find a neutral point with all this? These are just equations. Well, sort of, because there's a good thing. We wrote down this expression because we can actually measure the value of the deflection of the elevator at trim condition, and we can retrieve, so not measure explicitly, but implicitly, the trim value of the lift coefficient, granted that we know the altitude, the weight, and the airspeed. And of course, from, let's call it equation 6 over here, we can find the stability margin or the position of the neutral point, because SM is equal to minus CMCL, which is going to be equal to CM delta E, which is usually known, times this slope, partial delta E star, partial CL star. All right, so let's see how we can do that by simply measuring delta E star and CL star. So we start by selecting a center of gravity location. So we're just going to fly the airplane. We have the ability to rearrange the mass somehow in the airplane. So we know, or we have an estimation on where the position of the center of gravity is. So let's say that, for the sake of simplicity, the center of gravity is known. And we want to determine where the neutral point or the aerodynamic center is. So we need to find the static margin. So let's fix a location for the CG. Now, what we're going to do with that fixed, we're going to fly the airplane at different flight conditions. And for each condition, we trim the airplane so it flies level cruise. And we record the trim values for the elevator angle and the CL. And for each pair, we're going to put them in this CL delta E plot. So for each flight condition, we're going to have a different point with the same location of the center of gravity. So let's say we have one flight condition, second flight condition, third flight condition, so on and so forth. So by interpolating the data, we find a curve, and this is a straight line actually, and the slope of this line is delta, well, partial delta E, partial CL. That's something that we needed in order to find the static margin. But we're not done yet, because now what we're going to do is we redistribute the mass in the airplane so that we move the center of gravity a little bit aft, so towards the back of the airplane, towards the tail. So now we have a different location for the CG, and we repeat step 2. So we find a bunch of data with different flight conditions, and we find another slope of this curve. So we're going to find a bunch of curves for each location of the center of gravity. And as we move the center of gravity towards the back of the airplane, we're going to increase the slope. It's becoming less and less negative until it hits 0. But as I told you earlier, we don't want to fly the airplane at neutral stability because it's dangerous. So we can still estimate the neutral point without having to fly the airplane at neutral stability. So how are we going to do that? Well, after estimating the slopes for different locations of the center of gravity, so the slopes for all these curves, we're going to write down, we're going to record the slopes in this new plot as a function of the position of the center of gravity. So in this case, let's say we have these 5 data points, and then we extrapolate until we intersect the x-axis. Because in the x-axis, we have the location of the center of gravity, and in the y-axis, we have the slope of these curves here. So we know that when we have a flat line, that corresponds to neutral stability. So we know that we've hit the neutral point. So even without having to fly the airplane at neutral stability, by flying the airplane at a bunch of different flight conditions per location of the center of gravity, we can extrapolate from this data and find the neutral point. Okay, so this is all in terms of theory, and I just want to go over a numerical example. So this is actually the example 5.2 at page 198 of the latest handout that I posted. So the problem asks for determining the static margin, then the coefficient Cm alpha and Cm Cl when the normalized position of the center of gravity is 0.5. And here we're talking, we're referring to a Fairchild Republic A10, which is an aircraft from the 70s. And we're given a few more data. We're given the wing surface, we're given the horizontal tail surface, the mean wind chord, we're given the parameter eta h, the location, non-normalized location of the aerodynamic center of the horizontal tail, and we're assuming that the aerodynamic center of the wings and fuselage is the normalized one is at 1/4. This is usually a good assumption. Aerodynamic center, you might have heard, it's usually taken as 1/4 of the chord. And then we're also given the values of CL alpha H, and CL alpha WF. So we know that the static margin is the difference between the normalized position of the overall aerodynamic center of the aircraft minus the position of the center of gravity. But we don't know the position of the aerodynamic center. So we're going to use this big formula that we saw earlier. So we need to know all the terms. We actually have all of them as data except for the normalized position of the aerodynamic center for the horizontal tail, but we actually have it. We just need to normalize it using the mean chord of the wing. So that value is simply 2.98. So by plugging in the numbers, we find that the position of the aerodynamic center of the aircraft, or of the neutral point, either way, is 0.602. Now the static margin is going to be 0.602 minus the location of the center of gravity. So we have 0.102, which is positive. Therefore, the aircraft is longitudinally statically stable. What is CMCL? Well, that's just the opposite of the static margin. So easy, that's just minus 0.102. And now we're asked to calculate CM alpha. So CM alpha, from one of the formulas that I described earlier, is equal to minus CL alpha times the static margin. But what is CL alpha? Again, if you go up, if you refer to part 1 of the video, you see that you can retrieve this equation, which is a function of everything we have. So we can calculate CL alpha is equal to 0.0941. It should be, degrees to the minus 1, or 0.0941 CLs over degrees. So it's a rate of change of the CL with respect to alpha. All right, so CM alpha is that value. So minus that value times the static margin, which we found earlier. So we have that CM alpha is minus 0.0096, 1 over degrees, which is negative, and confirms, therefore, the positive static stability. All right, so I know this is quite intense, but I suggest you go through it with calm. If you have to watch the video again, or ask me questions if you had doubts, and of course read the handouts, because it contains exactly what I've covered, with even more details. Okay, so this is all for today. I'll see you next time, and take care.